All right, let's talk about Dijkstra's algorithm. This finds the cheapest path from a source node to every other reachable node in that graph. And I should mention that this is only going to work if you don't have negative edge weights. Because if you have negative edge weights, especially if it's a cycle of negative edge weights, and you're looking for the lowest cost, well, the lowest cost is negative infinity because you'll just keep going around that negative cycle. So in general, for Dijkstra's algorithm to work, you're not allowed to have negative edge weights. Now, the runtime of this algorithm is going to be big O of e plus n log n, where e is the number of edges in the graph and n is the number of nodes or vertices in the graph. I should make a couple of notes here. One is that I tend to use the term node when I'm referring to the nodes of a graph. I tend not to use the term vertex and vertices when I'm referring to nodes of the graph. The terms mean the same thing. I come from more of a networking background, so I tend to use node. People from a more mathematical background might tend to use the term vertex or vertices. One note about Dijkstra's algorithm is you're looking for paths, not edges. Now, the paths are made up out of edges, but at any given moment, what you're trying to find is the lowest cost path to any node that you have not yet visited. This is the key to Dijkstra's algorithm. Now, if you compare this with the Prim-Jarnik algorithm for minimum spanning tree, that algorithm, which is also a greedy algorithm just like Dijkstra's, is always looking for the cheapest edge that connects the current tree to an edge that to a node that you don't yet have in your tree. That's very different than Dijkstra's algorithm, where we actually have to consider the full path from the source node through some number of other nodes to the destination node. So we're going to walk through an example. We've got this graph here on the left. We're going to perform Dijkstra's. We're going to start at node A. Now there's a couple pieces of information we need to keep track of. First is this is our results here. This is every node, and this is the cost to get to that node from node A. You can see we can initialize this and say, well, to get from node A to node A, well, that's a cost of 0 because we start there. Down here, this is a priority queue. This is the lowest cost or cheapest path to any unvisited node that is currently reachable. So the first thing we're going to do, we're starting at A. Well, what's reachable from A? Well, we'll go ahead and add in all of the nodes that A has a direct edge to, which would be B, C, F, and D. And we're going to figure out, well, what's the cost of that path? Now, obviously, to get from A to C, this is both a path and an edge. There's a direct edge, but a direct edge is, in fact, a path. It's a path with only one hop on it. So we're going to put these into our priority queue. Now, technically, a priority queue may not be sorted from lowest to highest. The idea with a priority queue is that you can always get the minimum value thing out in constant time, and then if you put more stuff in there, it's log n to rebalance it in the worst case. But I'm just going to list this as sort of like a list that's sorted in reverse order, but you know, understand that in implementation details you would end up using something like a priority queue. So at this point, we're going to grab that cheapest edge, C, with a cost of 7. We're going to put that in here because if it's 0 to get to A, because we started A, well, we can reach C with a cost of 7. That's the lowest cost thing that's available for us to connect to. So we're going to put that in. We're going to go ahead and cross that edge off, and then we're going to figure out, well, what are all the things we can reach from C that we have not yet seen? Well, we can reach D with a cost of 17. We'll put that in. We can reach E with a cost of 9, right? The cost here, 7 to get to C, right? We know that, plus this edge to E, so that's a cost of 7 for the path from A to C, plus 2 to get to E. So the total cost to get from A to E is going to be 9. Similarly, to get to B would be 10, because we can go 7 plus 3. That's going to get us there with a cost of 10. And G would be 11, 7 plus 4. So all of those are based on taking C, the node that we've just solved, the one we just put into the table, looking at everybody that it's got a direct edge to, and figuring out, well, what's the cost to C? Once we know the cost to C, let's add the cost of C's edges to things that we haven't already solved. So now we're going to just repeat this process. What's the lowest cost thing that we haven't already visited that we can reach? Well, we'll pull this out, F. F with a cost of 8. F is now solved. We're going to put that in. Now we need to look at everything f can reach that we have not already seen. Well, f can get us to, if we can get to f with a cost of 8, that means we can get to e with a cost of 9, right? Because 8 to get here plus 1 to get here. And then we can also reach g with a cost of 10 because it's 8 to get here plus 2 to get here. And if you notice g with a cost of 10, that's actually bumped it ahead of this g with a cost of 11. So we've discovered a cheaper path by getting to c and then getting, figuring out the path to f and then discovering this better path here. Now, note that at this point, we have 2 ways to get to e with a cost of 9. We had the one we had already discovered where we went a to c and c to e, plus a to f and f to e. They both have a cost of 9. When we go ahead and pull the lowest cost one out, which one do we get? Well, turns out we actually don't care, as long as we only pull out one of them. Because all we're interested in is what the cost is. We don't actually need to know what the actual path is. We just care about the cost. The cost either way would be 9, so that's what's going to tell us. So we're going to go ahead and put that in there. What can we reach from E that we don't already know about? Well, E can get us to C. C's already solved. E can get us to F. F's already solved. So there's actually nothing new to add to our priority queue down here. So now we pull out the next thing. Well, that's E with a cost of 9. Well, we already had E with a cost of 9, so who cares? We already know how to get to E. We're just gonna go ahead and skip that because we already have a path to E, and it's going to have a better cost. This is what's a little bit subtle about Dijkstra's algorithm. The first time you pull something out of your priority queue and it's a path to something that you haven't already discovered a path to, by definition, that will be the best path to reach that. The reason for that, if there were a better path, you already would have discovered it. Now, this is a little bit subtle, but at any given moment, you're taking the path to the node that you have the cheapest total, that you have not visited, that you have the cheapest possible cost to get to. So that means that any lower cost path to any one of those nodes would have had to have taken a different process. Well, if you had followed a different sequence of nodes, then you would have found whatever the lower cost is. So, for example, here, if I'm at A, right, what can I reach from A? Well, I can reach F, I can reach D, I can reach B, I can reach C. Those are what the costs are, 7, 15, 11, 8. Now, to get from A to any other node through these nodes, any node that's not directly connected, like, for example, E, it's going to have to go through one of these other nodes. Well, A to C, that's our lowest cost, so we're going to explore that first. At that point, we've already have a cost of 7. Anything else we reach is going to have to be bigger than 7. If there were a cost to some other node, like, for example, E, that's going to be lower than the 9 that we discovered, well, it would have to use an edge out of A with a lower cost than 7. But if there were an edge from A with a lower cost of 7, then we already would have explored it and discovered this better path to E. So if from A, we could remember there's no negative edge weights. So if what we pick is this edge to C, well then this cost to E of 9, that's going to be the best thing that we find. So when we pull this second E out of the priority queue, if we already have E in our table, we can just ignore this one because it will be equal to or greater than the cost of the path that we already discovered. Because if there had been a better path, we already would have discovered it. It's kind of subtle, but it's very important. So anyway, we can skip that. Next, we're going to pull out B with a cost of 10. We'll throw that in. What can we reach from B that we haven't already visited? Well, nothing. We already have a cost to A. We already have a cost to C, so skip it. We're going to pull out G with a cost of 10. We'll throw that in there. That's 8 to get here plus 2 to get there. Can we reach anything from G that hasn't already been solved? No. We're going to pull out D with a cost of 11. Now we're going to solve that. That's actually this direct edge. So we go ahead and put that in. And now at this point, because everything here already has a cost, we can actually stop looking through these edges. At this point, we are, in fact, done. And so that is Dijkstra's algorithm. It's a greedy algorithm, meaning at every given moment, we just pick whatever the lowest cost path that's in our priority queue that leads to a node that we have not already discovered a path for. We just keep doing that every time. It's a greedy algorithm, but it turns out that this is, provably optimal, assuming that there are no negative edge weights. Excellent. Thanks very much for listening.